In this video, I want to quickly work some problems with regard to Chapter 1, dealing with density, scientific notation, significant figures, and calculations using significant figures. And this is from an old worksheet that I made a few years ago and used to teach. And so I thought it would just be good to work this for a few example problems. If you notice, I have the answers to some of these here for you. So number 1, determine the density. And they give you the mass and they give you the volume. And so if you remember, the formula for density is equal to mass divided by volume. So in this case, you have 149.8 grams, that's your mass, and then your volume is 12.1 milliliters. A common unit for density is grams per milliliter. And that's good because in this case the problem gives you grams and the problem gives you milliliters. But remember, if the answers were to be in grams per liter, then you would have to take this number 12.1 milliliters and convert it over to liters. And so the answer, if you divide these two things, would be answer choice C. 12.4. So maybe you should pause the video and see if you can work number 2. Again, the formula for density is mass divided by volume. But in this case, they're not asking for the density, they're asking for the mass. They give you the volume and they give you the density. So let's derive the formula. Density is equal to mass divided by volume. Doing algebra, we know that we can say the density times the volume is equal to the mass, which is exactly the rearrangement that we're looking for. So if you multiply the density, 9.77 grams per milliliter, by the volume, 88.6 milliliters, right? Notice that the milliliters is in the denominator here. It's in the numerator here, and so they cancel out. And that leaves you with units of grams only, which is fantastic because that is the units of the answer choices. Multiplying these two numbers will give you 866 grams, which is choice E. Moving forward, now the problem is asking you to write the following numbers in scientific notation. Now, scientific notation is simply a way that you can rewrite numbers and you can get it in an easier to read form. For instance, 1,750,000 is much easier to write as 1.75 times 10 to some power. So the trick is you need to keep all non-zero digits written out. So you have 175, you need to write 1, 7, and 5. Now let's count zeros. 1, 2, 3, 4, and then we'll move it over even further to the first digit in the number. So you got 1, 2, 3, 4, 5, 6. 1.75 times 10 to the 6. So let's check our work. If we move the decimal places, if we move the decimal over 6 places back to the right, we should get this original number. So let's see. 175, and we had 1, 2, 3, 4 zeros. So 1, 2, 3, 4, 5, 6. So that's how you know if you have written the number correctly in scientific notation. Now let's try 10,000. Well, we've only got one number that's non-zero. So we can say 1 times 10 to the what power? Well, assuming the decimal is at the very end here because it's not present, 1, 2, 3, 4. 1 times 10 to the 4. Looks like you have a little glitch there. It's interesting. So now the number 12. Well, the number 12 is already written in its most simple form. So now we have 0.0001. So we're going to do the exact same thing as we did in the first two, but backwards this time. If you move the decimal over 1, 2, 3, 4 places, you get just a regular whole number. In fact, you get the number 1. But since this time the decimal is to the left, or all the zeros in the decimal is to the left instead of the right, as in these examples here, it will be 1 times 10 to a negative number. And in this case, it would be -4. And finally, we have the 0.030071. It's the exact same concept as the previous example. We'll move the decimal after the very first non-zero digit, as you do in any example, no matter if the decimal and the zeros are to the left or to the right, and then we'll write out the number since it includes non-zero digits. So we'd have 3.0071 times 10, and this time it'll again be to the negative power because the decimal place is to the left, to the -2. Now if this 7-1 wasn't included, you could write 3 times 10, right? But you have to include the 3 and the 0.0071 because even though you have 2 zeros sandwiched in between, they're significant due to these, when I erased it, due to the non-zero digits to the right. So I'm going to clean this up just a little bit. You can always back the video up if you need to see this worked out again. Now let's move over to significant figures. And I'm going to change my laptop screen for just a second because I want to show you something. There are a lot of rules out there that you can memorize, but I don't see the point. The easiest thing that I know to use to memorize significant figures or the rules for sig figs is called the Atlantic-Pacific rule. So we know where the Pacific Ocean is located. We know where the Atlantic Ocean is located. And so here are some basic rules. Let me move over back to the iPad screen, and I'll change it here so you can see my little graphic here. By the way, this is from kentchemistry.com. I want to be sure that I credit everything correctly. If the decimal is present, so in this case the decimal is already there, you start counting digits from the Pacific or the left side, starting with the first non-zero digit. So in this example, the decimal is present, and every number beginning with the first non-zero digit on to the very end of the number is significant. So in this case, you have 0, 0, that doesn't matter, but you have 3, 1, and so any number including this 3, but after this 3 is significant. So you have 4 significant figures. Let's look at the example with the Atlantic. If the decimal point is absent, absent, hence Atlantic, and then again present Pacific, you start counting on the Atlantic side, and every number that is non-zero on to the end of the number is significant. So you have 31,400 in this example. The decimal is absent, so you start on the Atlantic side. You start counting your sig figs at the first non-zero digit. So this is not significant. This is not significant, but you have these digits, and so you have 3 sig figs. Let me explain something though. If there were to be a 0 here, which would be a weird number, it would still be significant because you start counting at your first non-zero digit and you move all the way on to the end of the number. And so that's what I use when I teach the Atlantic-Pacific rule, and I ignore all those hard rules that they want you to memorize because frankly, as long as you can work the problem correctly, it doesn't matter. So number 4 says list the number of sig figs in the following numbers. And so in this case, I'll work top to bottom. You have 246.32. Well, the decimal is present, so you start on the Pacific side, and you start counting your sig figs at the first non-zero digit. So in that case, all 5 numbers are significant here. All 6 numbers are significant here. The decimal is present, so you start at the 1 on the Pacific side. 1, 2, 3, 4, 5, 6. Oops. In this case here, the decimal is present. You start on the Pacific side, and you start counting your number of significant figures beginning at the first non-zero digit. So all 4 numbers here are significant. So the decimal, as you can see, is present in most of these. But the next example, you have to remember that you start counting at the first non-zero digit, because the decimal is present here, but the first non-zero digit is the 6. So in this case, you only have 3 significant figures. Let me work a few over on the far right-hand side where the decimal is absent, and then maybe you can pause the video and finish them. Let's look at the very top here. You have this big number. The decimal is absent. So you start counting your significant figures beginning on the Atlantic side, and you start at the very first non-zero digit. So in this case, you have 1 significant figure. Now, there can be exceptions with this. Say that you had 700,000 pennies. Well, each penny would obviously be significant. And this is something we call the absolute case. And your teacher will specify the exact way that he or she wants you to define significant figures in this case. Again, if you had 700,000 pennies, each penny would be significant. But if you only use the rules for sig figs, using the Atlantic Pacific rule, starting at the first non-zero digit moving from the left to the right, from the right to the left, you'll have 1 sig fig. It's the same in this example here. Using significant figures, they would all be significant, starting at the Atlantic side, moving from your right to the left. So even if you wanted to bring out the absolute case, all numbers are significant here, no matter what. So maybe you should pause the video and see if you can work the examples that I have not worked yet. Alright, so you have 1.008, the decimal's present. You start on the Pacific side, that is the left moving to the right. You count all numbers that are non-zero, and they're significant. So this 1 is significant, meaning all 4 here are sig figs. In the next example below, the decimal is present. Starting at the first non-zero digit, which is 3, and moving on will give you 3 sig figs. In this case, you start on the Pacific side, meaning the left-hand side. Starting at the first non-zero digit, it is 1, and so every digit after that is significant. You'd have 1 sig fig here. In this case, the decimal is present. The very first digit is non-zero, so all are significant. Just in case you need some extra clarification, if the decimal were not present here in this example, so I'm putting a little box here to mark that I'm talking about this example. Say the decimal wasn't here, it was right here. Then you would start at the Atlantic side. Well, say there wasn't any decimal at all actually here. You start at the Atlantic side, you would start the first non-zero digit, which would be the 7, and moving on. Then you would just have 5. So I'm just trying to show you the difference in the rules here. Whoops. In this next example, the decimal is present. Start at the first non-zero digit. So you have 1 significant figure in this case here. So there's sig figs. Now let's talk about adding and subtracting with significant figures. And then I'll close this video and we'll do another one separately on dimensional analysis. Express the answers to the following calculations in the correct number of significant figures. So I'm going to work A and B here just because I'm running out of time. And if you can do A and B, you can certainly do C and D. There's nothing wrong with using a calculator in these problems. You just have to remember the rules. When you're adding and subtracting, as in A, you cannot have any more digits or decimals than you had in your smallest number. And so that may be confusing, so let me write it out for you. You have 105.5 liters plus 10.65 liters. So in adding and subtracting, you're really only concerned with the numbers that come after the decimal place. In the 105.5, you have one number after the decimal. In 10.65, you have two numbers after the decimal. So in your final answer, you can only have the smallest numbers after the decimal. So you can only have one number after your decimal in this case. Adding this up in the calculator or in your head gives you 116.15 liters. But again, you can only have as many numbers after your decimal as you had in your smallest given value. In this case, it's 1. So it's going to be 116.2 liters. If it's 5 or up, you round up. If it's 4 below, you round down. Again, that's the rule for adding and subtracting. Now let's work B with multiplying and dividing. So the rules for multiplying and dividing are just a little bit different. Instead of worrying about the numbers that come after your decimal, you worry about the total amount of numbers in each of the given values. So you have 1.255, that's 4 values. Again, you're not worrying about numbers after the decimal in multiplication and division, times 25. Now if you put that straight in your calculator, I believe you're going to get the number. Well, I actually don't have a calculator with me. But if you were to multiply this out, you're going to get more than 2 numbers. You can only have 2 numbers in your final answer because you only have 2 numbers in your smallest given value. Again, this is in a multiplication or division type problem. And so if you plug it in the calculator, you're going to have to reduce it to only 2 numbers. That would be 31. So I'm going to pause the video here, and we'll work the dimensional analysis problems in another video for time's sake. Thank you for watching. Hope this helped, and have a great day.